Let me thank the organizers very much for the chance to visit this special place and hear some beautiful talks. I'm only going to talk about two optical effects in chiral materials, one linear and one nonlinear. And what I have to say kind of follows on the preceding talk. Suppose you have an effect that is allowed by symmetry. You could ask, what's interesting in the strength of the effect? Like, how does the material determine how strong the effect is? And is there ever any quantization or something like that interesting about the strength? So the two effects I'm going to talk about, I'm a theorist, so I do have one or two equations sprinkled in, but I tried to make it only equations that are worth knowing. So there aren't really derivations, but you can ask, and I'd be happy to talk more later. The two effects, one of them already appeared in the previous talk, which is optical activity. If you have a chiral material, or even chiral sugar molecules in water, say, then the plane of polarization of light can be rotated when it passes through the material. The second is a little bit more modern, where people discovered around 2015 some new three-dimensional materials called vial semimetals that are one kind of three-dimensional version of graphene in terms of their electronic structure. And I'll remind you why graphene is interesting optically in just a moment. But it took a while to try to figure out what is something special that these semimetals do. And I think one answer, at least one good answer, is they have a special kind of photocurrent that's actually the first example of something roughly quantized in nonlinear optics, but only roughly. And the introduction I have, since topology has appeared a lot, and also a bit of geometry, I want to explain how it appears in my field, which is crystals, basically, solid-state quantum condensed matter. Because there's been about a 40-year program with a couple of Nobel Prizes in trying to understand what are topological materials, how do their electrons behave differently than normal materials, and I'll try to sketch that at a very high level as my introduction. But first, I only have a couple of experiments in the talk, and my favorite one you can do with your hands, and you can measure something fundamental about the universe as long as someone gives you a sheet of graphene, which is not that easy, but if someone gives you the sheet of graphene, you can hold it up to the light, and you can mostly see through it. It blocks about 2.3% of the light in the visible. And that sounds a bit arbitrary, but 2.3% is pi times 1 over 137. You might have heard 1 over 137 is the vacuum, the fine structure constant of nature, of electromagnetism, that is. And note that what appears, it's really the vacuum fine structure constant. It's the speed of light. It's not the speed of the electrons in graphene. About the shortest paper in science that I've seen in recent years is this one by Andre Geim's group, which basically says we looked through graphene and it blocks 2.3% of the light like it was supposed to. The reason why graphene is special, this is a two-dimensional atomically thin sheet where the electron effective mass is 0. In fact, the electrons have sort of a linear or relativistic dispersion relation. Now that we have three-dimensional versions of graphene, which also have that linear dispersion, what might they do? And that's something we spent a few years on, and that's kind of the second half of the talk. So this was work with a number of people. The top line are the theorists who were in Berkeley and are now scattered around the world. Takehiro Morimoto is now at Tokyo, University of Tokyo Applied Physics as a faculty member. And I will talk about the experiment, which was done by groups led by these three people. So as background, a lot of what we think about is symmetry and symmetry breaking. And that's very powerful, as you saw in the preceding talk, not just to understand what effects are allowed, but there are even some very deep numbers related to symmetry breaking. So I just put up some examples of symmetry breaking at the bottom. I think we heard a lot about symmetry breaking in the previous talk and more subtle examples than these. But one thing that made me want to be a condensed matter physicist was the remarkable property that some numbers called critical exponents at symmetry breaking phase transitions are very universal. And one famous example, if you looked at the boiling transition in water, there's a point where the boiling transition disappears, some critical point, and you can measure how it disappears through the difference in densities. If instead you look at a different kind of transition, which is just a bar magnet like iron, there's again a Curie temperature where the magnetism disappears. If you look at how the magnetism disappears near its critical point, and how the liquid-gas difference disappears near its critical point, they both go with some power law. And the remarkable fact is it's the same power law. It's some number that is like pi or e, except it's a physics number rather than a math number. We don't have an explicit form, although actually people have gotten very good at getting more decimal places theoretically in recent years through conformal bootstrap. But that kind of universality at second-order phase transitions is very nice. There's a different sort of universality that's almost simpler in topological phases, where you might measure a magnitude of some fairly simple quantity that doesn't care about all your microscopic details. It's very universal. And the first example of this was the quantum Hall effect. So the Hall effect is a very basic measurement that people often do when they have a new material. You take your material, you apply a big magnetic field, you run a current perpendicular to the magnetic field, and you measure how much voltage gets built up because the magnetic field is bending the charge carriers. And normally, at weak magnetic fields, you get a sort of straight line dependence in the so-called Hall resistivity. But if you take two-dimensional materials and you go to large magnetic field, you get these plateaus that are very flat. In fact, they're flat to parts in a billion near the center. And if you measure, what is the magnitude, let me convert it to a conductivity, you get an integer times e squared over h to about 1 part in 10 to the 9th. This is the bare electron charge, and this is Planck's constant. So in other words, it doesn't care whether it's graphene or gallium arsenide or whatever. It's very universal, some simple number. The quantization of light passing through graphene is only maybe 1 part in 100. Here, it's 1 part in a billion, basically because this is an insulator, a gapped system. It has no diagonal conductivity. The green curve is the diagonal resistivity, and the conductivity are both equal to 0 on one of the plateaus. So what causes this? This is, again, the first example of a topological phase. And there's a picture that maybe people didn't pay that much attention to for a while by Thouless, but it turned out to be crucial for many other things in recent years. And that was at least a piece of why Thouless won a Nobel Prize. And how this is going to connect to optics is the following. So in general, symmetry tells you whether a response is allowed in a material. And if it's allowed, it should be there. That's kind of a principle maybe due to Landau. The examples that are relevant to optics, maybe, the most relevant ones, if I break inversion in a material, that will allow second harmonic generation, meaning light could come in at omega, and I will measure light coming out at 2 omega, twice the frequency. Polar materials are a subset where there's a preferred direction in the material. That's like what you would want for a solar cell, because a solar cell should take unpolarized light from the sun and produce current along a particular direction, so the direction has to come from the material. And then chiral materials, you all probably have worked on more than I have even. So chiral materials are a different subset of inversion breaking materials with no mirrors. So symmetry still works, and it's probably the most important principle for complicated matter. Geometry and topology that I'm going to tell you about in a second basically tell you when is the magnitude of some effect either very simple and only depending on geometry, or even simpler still because it's quantized and related to some topological invariant. So to make kind of a classical geometrical analog of what I'm calling geometry and what I'm calling topology of wave functions, just think about surfaces two-dimensional surfaces embedded in 3 dimensions. So if I go to one point on such a surface, there are 2 radii of curvature in perpendicular directions, and I can define the Gaussian curvature with a sign as 1 over the product of the radii, and the meaning of the sign of the Gaussian curvature is that if both curvatures are in the same sense, like both toward me or both away from me, like the sphere, that's positive Gaussian curvature. If one is toward me and one is away from me, like the hyperbola, that's negative Gaussian curvature. And the cylinder, even though it looks curved in the way we use the word, it actually has 0 Gaussian curvature. Now, the way geometry is related to topology in materials is something like the following well-known fact about surfaces. If I take this sphere, the Gaussian curvature is 1 over r squared, where r is the radius, and the surface area is 4 pi r squared. So the integral of the curvature over the surface is just 4 pi. And the magic is that if I took that sphere and I squeezed it into an egg or a football, as long as I don't tear it, I will still get 4 pi. So in a sense, the integral of the curvature gives me a topological invariant. If I took the torus, the zero curvature on the inside, the negative curvature on the inside cancels out the positive curvature on the outside, and the total curvature is 0. So that's a sign that the torus is not continuously connected to the sphere. So let's try and do something like that with electronic wave functions, because it turns out to give the Thouless picture based on Berry phases or geometric phases of the quantum Hall effect. So you need to know only one fact from solid-state physics. If I think about electronic wave functions in a crystal, so wave function is some function of space-time, complex function that describes my electron. When I go into a crystal, I can write it in a simple way. It's a product of a plane wave and some part that is periodic with the periodicity of the crystal. And often we write this, and then we don't actually use this periodic function very much. It's kind of the structure of the wave function inside the unit cell. But this will be the hero of what I have to talk about mostly. So this U is kind of the way the wave function is behaving inside the unit cell, what makes it different from a plane wave. If you just plot band structure or something, you don't really need to know what U is. You can just plot E versus K. So I'm going to make a kind of curvature out of these wave functions. And that will be my curvature, like in the Gauss-Bonnet theorem I just told you about. I also need a surface. The surface is just the allowed values of K. And you might remember in a crystal, I don't need to let K run over all three-dimensional space or two-dimensional space for a 2D material. I can restrict it to the first Brillouin zone, which is like a D-dimensional torus. So how do I make a curvature, and what's this Berry phase? Very briefly, the reason for talking about this is this kind of 40-year project going back to work of Thouless around the early 80s turns out to explain the quantum Hall effect. It had kind of a rebirth and turned out to explain many other things, including these topological insulators and things like that. Even if it's not quantized, it turns out that Berry phases are the heart of the modern theory of electrical polarization and magnetoelectricity and things like that. So there are a lot of cases in insulators. What I want to focus on are actually some new things related to metals. And don't worry, I'm talking about newish stuff, but maybe the original effects were worked out here, but it wasn't realized when they're especially interesting. All right, so the idea of the Berry phase is, in general, in quantum mechanics, we have a very powerful theorem called the adiabatic theorem, which says that if you're in some quantum state and there's no degeneracy, then if I change the Hamiltonian slowly, I remain in that quantum state. However, that's only a piece of the story. And one of the examples of a geometric phase that Berry gave is that if I were to take the Hamiltonian around some path in parameter space, so this could be like you twist your knobs in the laboratory, or for us, the parameter space is actually going to be momentum in the Brillouin zone, then I can write a phase that builds up in terms of something I'm going to use the symbol of a vector potential like an electromagnetism, but it's a vector potential that is just made out of how the wave function evolves with parameter. And my only mathematics of the Berry phase is going to be to try to convince you that it's not an accident that we write this like a vector potential. In fact, if you remember your classical electromagnetism, something like that is going on here. Because we heard, I think, in the very first lecture by Professor Dennis that overall phases in quantum mechanics shouldn't matter very much, which means that if I define the Berry phase with one wave function at each k point, and you define it with some other phase convention, like our wave functions are related because we're really talking about the same physical state, but we have some complicated relationship, I will assume that it's differentiable, between our phases, then what happens to this vector potential? Well, you can crank through the derivative, and you and I will disagree on the Berry connection, this A thing. We'll disagree by the gradient of the phase. But just like in electrodynamics, we know how to make things out of A that are gauge invariant, where here gauge is kind of like phase choice. So the simplest one is the curl of A, which is kind of like a magnetic field. In crystals, we call it the Berry curvature. And in fact, you can even get, like the magnetoelectric effect I mentioned, turns out to be controlled by the non-abelian generalization of this to multiple bands. So now let's come to metals. So maybe the key fact for insulators, which I somehow skipped the slide, if I take the Berry curvature and integrate it over a two-dimensional Brillouin zone, that will give me an integer, and that's a topological invariant. And that topological invariant tells me if I put electrons into that band, how much does it contribute to the quantum Hall effect. But today we're focusing on metals, and it turns out that in metals, the effect of the Berry curvature is even simpler. And in fact, well before Berry, closer to the time of Pancharatnam, it was discussed by Karplus and Luttinger, but they couldn't really explain it that well, maybe in hindsight, because the geometric ideas weren't so clear. But they basically pointed out that in low symmetry crystals, anything that breaks either time reversal or inversion, there's actually a missing term in the standard equation of motion that you find in classic books like Ashcroft and Merman. So the idea of the extra term is that there's an extra piece of the velocity that involves the Berry curvature and how the momentum is changing in time. And if you like, this makes it look a lot like the Lorentz force. So if you were describing a wave packet in a metal, there'd be this equation, but there'd be another equation that the momentum is changing, like E plus V cross B. This is kind of like a momentum field, a magnetic field acting on the momentum. What's happening, if you like, the picture of the anomalous velocity is that maybe at one momentum the electron is sitting on atom A, and at another momentum it's sitting on atom B. Then if the momentum is changing, the electron is kind of moving within the unit cell from atom A to atom B, and that's an extra piece of the velocity that only exists because the electron is not a plane wave. It has structure inside the unit cell. So there's been a long process, and it's not that easy, actually, of looking for experimental signatures of this term. The reason why it was originally discussed was to explain some experiments from about 1890, not 1990, the original experiments of Hall on the Hall effect. It turns out that optical experiments are a very nice way to probe this more directly. And then it turns out there's a sort of special case in these new semimetals. But I want to talk now, this is kind of the meat of the talk, about different optical effects in metals and how they're related to geometric and maybe even topological terms, kind of like this one. So first, as I mentioned, the anomalous Hall effect is sort of Hall effect in magnetic metals when it's not quantized, and that has a very long history, and it's still a very hard problem. You can tell it's hard. There's a classic review article by Naoto Nagosa. Even by the time they get to figure 47, they still have a speculative and schematic phase diagram. So the reason why it's kind of a hard problem is that if you make your metal very clean, you see Fermi surface dominated effects like ordinary semi-classical scattering. If you make your material very dirty, you get localization and you can't really think about momentum eigenstates. But there are about 3 orders of magnitude in iron, say, when what you measure in the Hall effect is more or less this intrinsic geometric term. So it's not quantized because I don't integrate over the whole Brillouin zone. I only integrate over the occupied states. But it is intrinsic or geometric in the sense that it only involves the Berry curvature. It doesn't involve the details of scattering or energetics or anything like that. So we call terms like this that are not quantized but don't have any dependence on energetics or scattering purely geometric. So the way I first got interested in optics and Berry phases was because I had an experimental optics colleague, Joe Orenstein, who kept bugging me about some experiments that had been done largely by a group in Germany on something called the circular photogalvanic effect, which in 3D you could call a chiral photocurrent. So the 2D version of this, imagine I have a ground state of electrons in a two-dimensional metal, which is the black circle. And I apply low frequency circularly polarized light. So what that light will do, well, the electric field will push the electrons away from equilibrium to the dotted circle, and then the dotted circle will slowly rotate around the ground state because of the circular polarization of the light. And you'll probably believe that when I do that, the ordinary velocity averages to 0, but the anomalous velocity doesn't, the Berry phase piece. And we believe that all those old experiments are actually controlled by the Berry phase, and there's some evidence for that. What I want to focus on in this talk, so I'm going to come back to this one because this is the effect which is a photocurrent, so it's like shine light, produce a current. That's second order, or nonlinear optics. I'm going to come back to this later because this effect turns out to be much deeper when you try these new Weil semimetals. The other effect that I want to talk about is just linear optics, and it's this old optical rotation effect. And there, we got interested because people proposed that something very unique would happen in linear optics in Val semimetals. And I don't think that's true. I think that what they proposed is actually there in all chiral metals, and not particularly quantized. And that's kind of the story in these two papers. This is ours, and it was worked out independently by these people. So that's kind of why we have to go to nonlinear optics. I actually think that linear stuff in Val semimetals is not so different from other materials. But basically, the effect is just, if you take a material which is chiral, like quartz or selenium, and you pass light through it, you rotate the plane of polarization. It's like the Faraday effect, but this is a non-magnetic material, and as a result, it has an extra power of K. So, as I mentioned, we got interested because people were saying that there was something like a solid-state version of the chiral magnetic effect that I saw some posters on in nuclear physics. And the way they would write it is that a magnetic field produces a current. I don't really like this because it's not true in the static limit. If you let the magnetic field vary in time, it is true. But a time-varying magnetic field produces an electric field. So you're really just talking about an electromagnetic wave. And that's why the so-called solid-state chiral magnetic effect, at least in linear response, is optical activity. And I'll preview the formula and then just try to explain it. Basically, the Berry phase, that standard geometric object, does not appear in low-frequency optical activity in a metal. What does appear is just the integral over the Fermi surface. This is complicated notation maybe, but it's just summing over bands, integrate over the Fermi surface. This is the Fermi velocity. And this m is the hero of the story. It is the orbital magnetic moment of Bloch electrons, which is something that I never learned in solid-state physics, but it turns out to control optical rotation at low frequency. And I'll tell you a little bit more about what that quantity is and why it matters. And this is a case where we did a very serious quantum calculation that led to 8 pages of supplemental material, and then realized that a very simple semi-classical calculation gives you the right answer. So when you go into a crystal, you have Bloch states, which are some superpositions of atomic orbitals. And we know that atomic orbitals can have both a spin magnetic moment and also an orbital magnetic moment. And then maybe it's not surprising that when you look at a Bloch state, again, different momenta are different superpositions of atomic orbitals. That means that the orbital momentum will change as the momentum changes. So this m will be a function of momentum. And actually, the mathematical object, this is the expression, which is not so easy to derive. It's some derivative of, this is the same thing as the u I wrote before, but now with the band index. And this is the Hamiltonian. It's basically the Berry curvature plus an extra power of the Hamiltonian in the middle. So that's not very obvious, but somehow the magnetic moment of electrons in a crystal is fairly closely related to the Berry curvature. We would not call it purely geometric because it has this energy factor, but it has geometric content. And the reason why it matters is just this. I told you about the anomalous velocity, which is one big thing that happens when you go into a crystal from geometry. But a second thing is that even the group velocity, which is just the momentum derivative of energy, think about how that's going to work in a magnetic field. So there'll be an extra term, which is magnetic moment dotted into magnetic field. But if the magnetic moment depends on K, then this contributes when I take the derivative. In other words, not just the anomalous velocity is sort of geometric, even the group velocity in a magnetic field has this orbital moment piece. And when you work out just the semi-classical response, you find that everything else vanishes and you're just left with this as the low-frequency determinant of optical activity in chiral metals. So that's not so great from the point of view of Val semimetals, and now is when I tell you about what a Val semimetal is in more detail. But it's exciting that this very old measurement has sort of a geometric, simple meaning at low frequency. So the idea of a Val semimetal, if you go back to the early days of quantum mechanics, Dirac famously wrote down a relativistic equation for the electron in 3D. And it's a 4x4 matrix equation, which in solid-state physics we would think of like 4 bands coming together. And people looked for those for a long time. Where do you have 4 bands that come together in a point at the Fermi level in 3D? And the first examples were found around 2013.
Soon after Dirac, Hermann Weyl pointed out a neat way that the Dirac equation can sort of separate. It turns out that if you have massless particles, you could have sort of right-handed particles and left-handed particles that would not mix. Because if you have a massive particle, then you can flip its helicity by Lorentz boosting to a frame moving faster than it. If it's a massless particle, you can't flip its helicity. Its helicity is Lorentz invariant. So you should really factorize the Dirac equation into two by two pieces. For a long time, people thought neutrinos might be Weyl fermions, but then they were found to be massive, so they can't be. But we do have a solid-state version, which is now a number of materials, but tantalum arsenide was probably the first, and those were found around 2014, 2015. So the reason why these are kind of topological, so I mentioned it's an old idea, goes back to Hermann Weyl, and people started finding the idea in the solid state context around the 1930s, but it was pointed out much more recently that a Weyl point, which is a two-band crossing in a 3D crystal at a point, has a topological content. It's basically a monopole of the Berry curvature. Shuichi Murakami, I think, might have been on the organizing committee or something for this meeting. He's the one who really explained that in solid state terms. And that as a consequence in terms of a surface state, it also has a consequence in terms of optics. And basically, something like this does happen when I go to nonlinear optics in Weyl semimetals. And I'm going to be very quick on the theory because I want to get to the experiment. The theory is motivated in several ways, but here's one way. If you look at the high energy posters or listen to one of the talks here, you'll have heard about the chiral anomaly, which we would say in condensed matter language is a problem with a single Weyl fermion. There's a reason why the total Weyl Fermi charge, in other words, the total monopole charge of all these Weyl points has to be 0. That's called the Nielsen-Ninomiya theorem in field theory. If it weren't, if you had a single Weyl point, say, you could actually create charge out of thin air by applying parallel electric and magnetic fields. So anomaly means like a problem with conservation in the quantum theory. So a single Weyl point would have an anomaly. If we have two Weyl points with opposite charge, say, then it's okay. It's like we pump charge from one to the other. But that's a sign that maybe you should look at nonlinear effects. Now, it's hard to make this happen at equilibrium in Weyl semimetals or near equilibrium. But sort of by power counting, there is a related effect. And a way to understand, this is not how we were thinking about it, but we could have in hindsight. If you took the two-dimensional quantum Hall effect and forgot about spatial indices, it's like saying a two-dimensional current density gets created by an electric field, and if you want to get the units right and only use fundamental constants, it has to be E²/h. What if you wanted to only use fundamental constants and get an effect that involved 2 powers of electric field? Well, by counting, you'd have to add another charge and another Planck constant, and it turns out that gives you one more inverse time and one inverse length. The inverse length makes it a 3-dimensional current density, and now there has to be a 1/time. But the rate at which current changes in time, if you work on photocurrents, this is known as current injection. It's like you shine light on a material, it produces current. So maybe there could be materials that have a sort of quantized current injection. And that's what some Weyl semimetals are. But before I get to that, even before we were interested in these chiral Weyl semimetals, even tantalum arsenide, which is polar but not chiral, has famously strong nonlinear optical response. Looking at Chi2, which is second harmonic generation, it's actually the most nonlinear optical material around, basically, in some frequency range. So that's a sign, just from experiment, that maybe nonlinear optics is interesting in Weyls. So what we did is go back to this effect, this kind of semi-classical effect, and now ask about what happens if I do it in this very special band structure. But this old calculation still winds up mattering, but we have to do a proper quantum calculation for the Weyl point. And let me maybe draw a picture of the calculation rather than doing it in detail, and then I'll put up the result in a second. The basic idea, if I took a Weyl semimetal like tantalum arsenide, which has mirror symmetries, there are a whole lot of Weyl points, I think there are 24, and at every energy where you have positive Weyl points, you have negative Weyl points at the same energy generated by the mirrors. In something like rhodium silicide, that will be the hero material for the experiment, it's chiral, and as a result, you can split, say, the positive Weyl point from the negative Weyl point in energy. and then put the Fermi level somewhere in between. So the green is filling up states to the Fermi level. Then what happens, if you think about optical transitions at some finite frequency omega, this optical transition across the val point is allowed. So I should compute it. And I can't compute it anymore with semi-classics. One of the principles of semi-classics is that the nature of the band structure should not be changing dramatically over the frequencies I'm interested in. So this one I have to do a proper quantum calculation, but it's not that hard. This one, though, we would say this transition across the val point is polyblocked, meaning just that we don't see it because the final state is filled, so I can't excite to it. I will see transitions up here, but basically, for this val point, I can use our old 2010 semi-classical effect, and we know that's non-universal and very weak. This one is, we need to do quantum mechanics, and what do we get? Well, the answer is the rate of current injection at a single val point. If you make transitions across the val point, it looks a little bit complicated, but nothing in here is material dependent except for one integer. C sub n is the charge of the val point, I is the intensity of the light, and these are fundamental constants, basically E cubed over h squared. So that means if you had a single val point and no interactions, you would get a quantized nonlinear optical effect at order E cubed over h squared. So the path from this to reality and materials and experiment took a couple of years. And to try to give credit where credit is due, we had a material proposal when we said someone should look for this effect and that it might be quantized. Our material turns out to be hard to grow as crystals, but at about the same time, Zahid Hassan's group found rhodium silicide, which has a pretty large gap between positive and negative val points, and it turns out it also has a charge of the val point of 4, so the effect is moderately large. And there is a nice paper by a bunch of youngish people figuring out how large would, in this new material, the quantized circular photogalvanic effect, this nonlinear effect, and the thing I talked about earlier, the gyrotropic magnetic effect, how large should those be, and maybe more directly measurable, what would their frequency dependence be in rhodium silicide? So at that point, people started trying to do an experiment. And here's the idea of the experiment, which is all optical, so no contacts. Basically, you shine a pulse of light into the rhodium silicide. That creates a brief burst of photocurrent. That brief burst of photocurrent, you can measure the radiation it produces and see, essentially, overall magnitudes are tricky to measure from the radiated field, but you can at least see, does this depend on frequency the way the theory would suggest? And the way theory should suggest this should work is very unusual as nonlinear optics goes, because if I go back to this picture, I should basically get the strong effect from transitions across the val point whenever the Fermi level is in between the two val points. And then once the frequency gets larger, I start to activate transitions across this one, and those cancel out the transitions across that one. So I should get a strong photocurrent up to some frequency, which is 0.7 electron volt in rhodium silicide, according to theory, and then it should turn off. And remarkably, so I'm showing the first experiment. There are a couple of later experiments on other compounds. That is more or less what happens. So the laser that they use kind of pukes out at low frequency, but there's a strong effect. And again, this number 0.7 EV was predicted before the experiment. So that was good work by those postdocs who are now faculty all over, including Morimoto, I believe. So it falls off pretty smoothly once you hit 0.7 EV. So that's this paper. So again, the magnitude is probably not quantized all that well. It turns out we tried to understand how large are the corrections from interactions in other bands, and it made me think that there is something cosmically lucky about graphene, which people work on graphene already kind of know, that many things in graphene are better than you would expect. So I'll mention this calculation, which I'm not going to talk about in any detail because this is real, honest, interacting quantum condensed matter physics, vertex corrections, and so on. You get a moderately large correction. So maybe a way to put it is val semimetals that are chiral should have a quantized nonlinear effect, but very weakly quantized. It's better to say that the natural scale of the effect is something like E cubed over h squared times an integer. In graphene, it is quantized to about 1%, But it turns out the reason is that the interaction corrections are there, and you would think they are order unity, but they're order 1% because a certain number is small. It took a lot of groups a lot of time to agree on the number, but the coefficient in graphene is anomalously small. It's 19 minus 6 pi, which if you think about that is kind of small, divided by 12. I don't know why, I don't think there's any deep reason why it had to be so small, but basically graphene, the corrections are small, and in 3D Val semimetals, the corrections are probably of order 20 or 50%. And then finally, so I've mostly talked about things that are a couple years old and that are not the sort of theoretical calculating and playing around with equations that we do, but to talk about one new thing, suppose you wanted to do nonlinear optics and not focus on the special case of Val semimetals and just ask, is there a nice geometrical way to represent some things in nonlinear optics? And we've written a couple of long papers in that style, and the most recent just came out on the archive a few months ago, and it's basically saying that nonlinear optical effects like the shift current, you can write in an explicitly gauge invariant way using projection operators. This is kind of related to a certain Riemannian curvature, and it also could maybe be combined with some previous work we did on diagrammatic formalisms for interactions. So this is just to show that we do some actual theoretical work for a living, and not everything is as simple as quantized or geometrical or whatever. So to wrap up, my first story, and it's great to be at a conference with people who think about chirality and things like that in all different fields, because I haven't had such a suitable audience in that sense before. If you go to low-frequency linear optics in chiral metals, which people have measured for a very long time, it's surprisingly simple, and it's entirely controlled by a certain quantity on the Fermi surface, and that quantity is just the orbital magnetic moment. Nonlinear optics is harder, but kind of interesting, at least in Val semimetals. In some materials, it's strong, basically because this material has a very strong skewness of the Wannier orbital, I believe. Not exactly topological, but sort of geometric. And in these special chiral semimetals, you get something that is quantized with corrections, but maybe the point is the natural scale is e cubed over h squared. And that means we can add one to the list of integer quanta and electromagnetic response. There are a lot of linear and E quanta, like the Josephson frequency or the quantization of flux in a superconducting vortex. There are a lot of E squared quanta already in this conference. E squared over H is the same G naught that appeared in molecular junctions. It appears in the quantum Hall effect and other things. Graphene optical transmission is like that with another power of the speed of light. And then finally, there's at least in the non-interacting world that we don't live in, there would be an E cubed over H squared quantum. So with that, let me thank you for your attention.